Let's look at this example. F of x is equal to x cubed minus 3x. Where does f have a horizontal tangent line? Okay. Yeah, there's a horizontal tangent line right here. And there's a horizontal tangent line, horizontal tangent line right here. Okay, so let's say at -1 and at +1. And how would you describe the graph at these points? Right here, and right here. And we'll get into the verbiage a little bit later, but you can sort of tell that at this point right here, that is the largest value that that function has in that little neighborhood. Okay, the function values increase, and then they reach this maximum, and then they decrease. Now, that's not saying that this is the largest function value ever for this function, but in this little area, this is the biggest one, right? And same thing down here. This is the smallest one in this little area. So this is going to be called a local max and a local min. Local max and local min. Okay. Be careful. I think your book also uses the term relative max and relative min. Okay. So relative and local are the same thing. All right. Now, how do we know how to find these things? What is the calculus behind all this? Let's look at this box. Consider f prime of x. The derivative of f gives us the blank of the graph of f at each point. What does the derivative tell us? One word. Slope. Yeah, it tells us the slope. Okay, and that slope may be horizontal. We don't know. But at every point, it's going to tell us what the slope is. It's shorthand for instantaneous rate of change. Now, what do we know here? If f prime is greater than 0, that is, if it is positive at some point, then the graph is doing what at that point? It is increasing. If f prime is negative at some point, then the graph is decreasing. And if f prime is equal to 0 at some point, then the graph has a horizontal tangent line at that point. Horizontal tangent line. So here all we're doing is exploiting the fact that the derivative represents the slope. If that derivative is positive, that means we have a positive slope. If you have a positive slope, that means you are increasing. If you have a negative slope, that means you are decreasing. And if you have a 0 slope, you have a horizontal tangent line. One word of warning, we always think about increasing and decreasing going from left to right. We never think about it going from right to left. Okay, so you always consider things left to right. Okay, increasing and decreasing. Let's look at example 2. The function here is x cubed minus 3x. It's the same one in the graph above. We want to find the derivative and then create a sign chart showing where the derivative is positive, where it is 0, and where it is negative. And then we will state whether it's increasing or decreasing. Now, so there's basically two types of sign charts you can use. I'm going to show you this one. This is the method that I've sort of created called the box method. You won't see this in the textbook, but it is a way to sort of organize everything and keep things sort of intact. You could also use the old-fashioned just straight line sign chart if you want to. Okay? So here, in order to find where the function is increasing and decreasing, we need to know what the derivatives are doing, right? The function is increasing if we can find where the derivative is positive, and the function is decreasing if we can find where the derivative is negative. It's as simple as that. Okay? So let's start with the function. X cubed minus 3x. We need the derivative. What is the derivative of this function? X squared minus 3. All right. This function is polynomial. In order to determine where a polynomial is positive and negative, we're going to do the sign chart. The only place a polynomial can change from being positive and negative is when it passes through a 0. So we're going to find where it's equal to 0. So I'm going to factor out the 3 to start with. That leaves me with x squared minus 1. How does x squared minus 1 factor? Yeah, x minus 1 and x plus 1. And then from here, I would set each of these factors equal to 0 and solve for x. When I set 3 equal to 0, we get nothing. If I set x minus 1 equal to 0, I get x equals 1. And if I set x plus 1 equal to 0, I get x equals negative 1. Notice that these are the two answers that you told me were the answers from at the top of the page. This is how you would work that problem out. Okay? So, these are what we call partition points. They're going to partition the domain into distinct intervals where the graph could have differing behaviors. That's what goes here in the points section, but they go on top. These are the partition points. Right? If you've ever worked in a big office building, you know how you have the partitions that separate each person's office? It's the same deal here. These go on top of these lines. Okay? The negative one represents this first vertical line here. The positive one represents this second vertical line there. Next, we think about the domain of the original function. Since this was polynomial, the domain is negative infinity to infinity. We write the intervals that are created by the separations with these partitions. So this first interval is negative infinity to negative 1. The middle interval is negative 1 to positive 1. And the last one is positive 1 to infinity. In the third row, we need to put down whether the derivative is positive or negative. We know that it's never 0 inside any of these intervals because I have already found where the derivative is equal to 0. It is equal to 0 at these 2 points and these 2 points alone. So we do the test, and we're going to test it in the derivative function. So we're going to pick a number from this first interval right here. I'm going to pick negative 2, and I'm going to plug it into one of the representations of the derivative. It could be this one, it could be this one, or it could be this one, because all three of these are equal to the derivative. Usually your best bet is to pick the factored form, because then you can just easily trace out what happens to the pluses and the minuses. At this point, I do not care what the number is. I just want to know the sign. So this 3, is that positive or negative? That is positive. This sum, positive or negative? Negative. And this sum, positive or negative? Negative. A positive times a negative is a positive. And that's what goes in the box there. Okay. And now we need to do it for the other 2 intervals. From this middle interval between negative 1 and 1, I would plug in 0. And this is going to be 3 times 0 minus 1 times 0 plus 1. If you work that out, that is going to be negative. And I need to pick a number from the third interval. I'll pick positive 2. And if you work all that out, you get a positive. As a reminder, the signs do not have to alternate. You can have two positives in a row. You can have two negatives in a row. This time it's just positive, negative, positive. Now we make the determination about what happens in each of these intervals. If the first derivative is positive, then what does that tell me about the function? Is it increasing or decreasing? It's increasing. To symbolize increasing, we use a slanted arrow going from left to right, going up. Okay? We will use a straight up and down arrow for something else later on in the week. So this one is a slanted arrow. On the interval from -1 to 1, increasing or decreasing? Decreasing. And on the interval from 1 to infinity, it is increasing. Okay. Now, I realize we're pretty much out of space here, but you do need to write the statements about what is happening here. Okay. So, somewhere along the deal, and I'll just write one of them. Well, maybe I can write both of them. This would be for this piece right here. You would say f is increasing on, and you pick up these two intervals with union. -infinity to -1, union 1 to infinity. And then f is decreasing on -1 to 1. Example 3, we have f of x is equal to 4x minus x to the fourth. We want to know where that function is increasing and decreasing. So we will take the derivative. And we get 4 minus 4x cubed. And we want to set this equal to 0. And then solve for x. And you could either use the difference of cubes on this, or you can just solve it straight out, like so. And so x is equal to 1. And so now we create the box. So we have the points. And in this case, we only have one point. Then we have the intervals. And we have f prime. And we have f increasing and decreasing. So we have -infinity to 1, 1 to infinity. We need to test the derivative at, let's say, 0. So that would be 4, so that's a plus. And then I can test it at 2. Again, you're choosing these numbers based on the intervals, 0 and 2. And so 4 minus 4 times 2 cubed. I don't know what that is, but it's certainly going to be negative. And then that means it's increasing and then decreasing. So you would write the statement, f is increasing on -infinity to 1, and f is decreasing on 1 to infinity. All right, the definition of critical values, and there are other terms that are associated with this. There's critical values and critical numbers. Those are just going to be x values, but then there's also critical points, and a critical point is going to be a whole point. So this would be values of x in the domain of f where either one of these two things happen. F prime of x is equal to 0, or f prime of x is undefined. Okay. Either one of these are going to be critical values, and they need to be considered in the box when we create the sign chart. Okay. So you're looking for where it's 0 or where it's undefined. All right, example 4. Find the critical values of f of x is equal to x to the fifth plus 3x to the fourth minus 3x cubed. So to find critical values, we take the derivative, find where it's equal to 0, and find where it's undefined. So the derivative of this function is 5x to the fourth plus 12x cubed minus 9x squared. What type of function is f prime? Polynomial. Polynomial functions are continuous everywhere. So therefore, this function is never undefined. Okay? So f prime is defined everywhere. So there's nothing to check on the backside here. There's no place where it's going to be undefined. So now all we need to check is where it's equal to 0. So we're going to set this equal to 0. What can you factor from all three terms? X squared. That leaves me with 5x squared plus 12x minus 9 equals 0. Then you want to try to factor 5x squared plus 12x minus 9. And sure enough, it's going to be 5x and x, 3 and 3. And 5x times 3 is 15, so that's the big one. So that's going to be plus. And this other 3 is minus. And then you would solve by setting each of these factors equal to 0. So we're going to get x equals 0. We're going to get x equals 3/5. We're going to get x equals negative 3. And these are the critical values. Find the critical values of the square root function. So what is the derivative of the square root function? 1/2 squared of x. So to find critical values, I first set it equal to 0. All right, so f prime equal to 0 would be 1/2 square roots of x equal to 0. When you have a fraction equal to 0, that is the same thing as having the numerator just be equal to 0. So we get 1 equals 0, which gives no solutions. So nothing to be gained there. The other side of this would be to find where f prime of x is undefined. To find where a fraction like this is undefined, you're going to take the denominator and set it equal to 0. If 2 square roots of x is equal to 0, what value of x makes this true? Yeah, it's just 0. Yeah. Divide by 2, square both sides, and you get 0. Now the only other question that you have to ask is, was x equals 0 in the original, spelled original wrong, original domain. One of the conditions on being a critical value is you are where the derivative is undefined, but it had to have been in the original domain in order to be considered. Is x equals 0 in the domain of the function f of x equals square root of x? Yes. Yes. Can you take the square root of 0? Yes. Yes. So the answer is yes, and since it's yes, then that means this is the critical value. Had we answered no to is it in the original domain, then it would not have been a critical value. It's not considered to be critical. All right. Let's talk about local extrema. Okay. The first thing you want to know is that extrema is the plural of the word extremum. Okay. This is the old-fashioned way of making words plural that end in um. Right? And we'll have these other words like maxima, minima, optima, things like this. All right. So local extrema refer to the local min, which is when the graph looks like this, right? Or a local max, which is where the graph looks like this. Local extrema occur only at critical values. Okay? So you can only have a local extreme at a critical value. But not all critical values result in extrema. Okay? So if you're going to have an extreme, then it has to come from a critical value. But simply because you have a critical value, that does not mean you're going to necessarily get an extreme value. Let's take a look at the example that shows this is the case. Example 6. Show that f of x equals to x cubed has a critical value, but no extrema. So to motivate this, first thing I will show you is the graph of x cubed, which looks like this, more or less. Can you see where this graph has a horizontal tangent line? Sort of. It actually has a slope right here at the origin of 0. So that's going to come up as a critical value. But it's not going to be an extreme, because it's going to increase all the way through that. So it's not a max and it's not a min. So let's show that. So first off, what is the derivative of x cubed? It's 3x squared. We're going to set that equal to 0, and then we're going to solve for x. So divide by 3, and take the square root, and you get x equals 0. So then if I draw the box, I draw the intervals, and we want to look at f prime, the key to looking at f prime is right here. Since you have 3x squared, because of the squared part, everything is always positive or 0. It's never negative. The only place it's going to be 0 is at 0 itself. So in these intervals, it's always going to be positive. For the function itself, that means this function is increasing followed by more increasing. If you are increasing followed by more increasing, then you don't have an extreme value. In order to have an extreme, it has to be increasing followed by decreasing, or decreasing followed by increasing. Here, it just keeps going. Okay? So this shows that we have a critical value, which is x equals 0, but no extreme value. So basically what this theorem above tells us about the local extrema is where to look for the local extrema. We're only going to find local extrema at the critical values, and that's it. All right, let's look at example 7. Find all extrema of f of x equal to x cubed minus 9x squared plus 24x minus 14. So to find the extrema, we need to take the derivative. The derivative is going to be 3x squared minus 18x plus 24. This function is a polynomial, so it is defined everywhere. So to find the critical values, all we need to do is set it equal to 0 and factor. So first, I notice that 3 will factor out of everything. That leaves me with x squared minus 6x plus 8 equal to 0. Next, I can factor x squared minus 6x plus 8. And that's x minus 4 and x minus 2. If we set 3 equal to 0, we don't get anything there. But from these other ones, we get x equals 4 and x equals 2. So I'm going to draw the box based on these two partition points. Also, they need to be drawn in order, number line order. So 2 comes before 4. So it's going to be negative infinity to 2, 2 to 4, 4 to infinity. Next, you need to test the derivative, and I'm going to use this factored form. That is the easiest form to use. So I'm going to pick 0 as the test point for the first interval. So this would be 3 times 0 minus 4 times 0 minus 2. That is going to be a positive. I'm going to pick 3 for the middle interval. Working that out, that is negative. And then I will pick 5 for the last interval. And that result is positive. So that tells me that we are increasing, decreasing, increasing. Now, where do I have a local maximum? At what x value? Yeah. This, x equals 2, is going to be a local max, because it is increasing followed by decreasing. Okay? If you have decreasing followed by increasing, that is a minimum. Now, the other thing that the book is going to want you to do is to find the extreme values. Okay? So if it asks for extreme values, that is the y values at the critical value for whichever one it is, and it is inside the original f of x, not the derivative. We know what it is at the derivative. It's 0. No, that's no good at all. So it wants the actual extreme value. So you would do that. Yes.